Hi everyone. So we're going to learn about how to predict whether there's going to be more product or reactant after equilibrium is established today by getting a look at equilibrium constants and reaction quotients. So let's say that we have a diagram like in the last chapter of chemical potential energy versus reaction progression. So we might start out with a bunch of A's, maybe 4 A's, and they might turn into some B. But they don't all turn into B. You see that this forward reaction is reversible. B can also turn back into A. Now, which of these is easier? Turning A into B or B into A? Well, it should be easier to turn A into B because the activation energy in that forward direction is relatively small. The difference in energy between the start point and the activation energy barrier is only yay big. But it's much harder for B to turn into A because in order to turn from B into A, the particles need to go from here to here. Much greater increase. So easy to roll over this curve, hard to roll over that curve. And so if we discount any orientation factors or kind of entropy issues, which we'll learn about later, then we might assume that we might get more B than A after equilibrium is established. And so we get this ratio of 3 B's to 1 A. When equilibrium is established, the amount of product over the amount of reactant in concentrations is equal to 3 in this case. That is the equilibrium constant. For a given temperature and reaction, there is an equilibrium constant. It's constant. It's always the same at that temperature for that reaction. So whether you start with a whole lot of A's or a whole lot of B's, or you start with a mixture of both after equilibrium is established, you should get a ratio of 3 to 1 in terms of the concentration of products to reactants. So you can learn a lot about a reaction by the value of that equilibrium constant. In this case, the equilibrium constant was 3. It was greater than 1 because there was more product than reactant once equilibrium was established. If K is greater than 1, products will be favored. There should be more products than reactants at equilibrium. If K is less than 1, then the reactants should be favored. There should be more reactant than product once equilibrium is established. So, as an example case, if K is equal to 2.0 times 10 to the negative 20, should there be more product or reactant? Oh, this value is much less than 1. It's like 0.00000000002. So K is less than 1, so we'll say reactants are favored for that. If you wanted a lot of product, that is not going to work out very well for you. You're going to get mostly reactants. So you might want to change the conditions of the reaction, maybe changing the temperature, so that you can get more product. So we have this ratio of product to reactant 3 to 1, whether we have to go over that entire barrier or even if there's a catalyst. If there's a new pathway, the size of the curve that you need to go over, just this new one, is smaller than before in the forward direction and also in the reverse direction. It's easier to roll over to the forward direction and it's easier to roll over to the reverse direction than before. And so adding a catalyst is not going to change the ratio of product to reactant once equilibrium is established. And equilibrium will not change the equilibrium constant. What does depend on, or what does affect equilibrium constant? It depends on just what temperature you have and what reaction you have. Doesn't depend on the presence of catalyst or surface area or the concentrations of a reactant or product. So let's go through a couple scenarios. Let's say that we start with 4 reactant particles and no product particles. Will we necessarily get 3 products and 1 reactant if we just leave these all in a pot? No. These particles may not be able to roll over that activation energy barrier. They may not be able to turn into product. And so you may not ever achieve an equilibrium. This is kind of like if you have a container full of natural gas and oxygen. That doesn't mean that it's all going to react, not without maybe a spark. So not all reactions achieve equilibrium. Sometimes you may need something like a spark or a higher temperature. Equilibrium not achieved for all reactions. Okay, so let's say that we start with 2 reactant particles and 2 product particles. I wonder which one we'll soon get more of. Are we soon going to get more product or soon going to get more reactant for the same reaction that we were seeing earlier? Well, 2 to 2. We kept seeing over and over that if we achieve equilibrium, we should get 3 products to 1 reactant. So that's what you should expect pretty soon. You will reach an equilibrium, 3 products to 1 reactant, if you were able to get the particles reacting, if you had a sufficient activation energy available. So we can predict whether the amount of product will soon increase or decrease versus the amount of reactant by looking at the reaction quotient. The reaction quotient is the ratio of the amount of product to reactant at a certain moment. Now, earlier we saw equilibrium constant was the ratio of product to reactant at equilibrium, but this is just at this moment. So at this moment, Q, the ratio of product to reactant, is 2 to 2, or it's equal to 1. So in this case, Q is less than the value of K that we saw earlier. Earlier we saw K was 3. If Q is less than K, that ratio of product to reactant will soon need to change to achieve equilibrium. Q will need to change to equal K. So if Q started as 1 but eventually needs to equal 3, Q will need to increase. If Q is less than K, Q will soon need to increase to achieve some equilibrium. And this happens by having the amount of products increasing. If you get a higher amount of product and a lower amount of reactant, then the ratio of product to reactant will increase. Q should change until it equals K. So, kind of summary, if Q starts out as being less than K, then you're soon going to increase the amount of product until Q is equal to K. So, yet at equilibrium, Q is now equal to the equilibrium constant. It's now equal to 3. Now, in another scenario, what if we started with all product and no reactant, and we allowed the system to reach equilibrium? So in this case, Q is equal to the amount of product over reactant, 4 over 0. That's infinity. So Q is now greater than that K value of 3. If Q is too high, it needs to decrease until it ends up being equal to K. Q can decrease by decreasing the amount of product and increasing the amount of reactant until you reach equilibrium again. 3 products and 1 reactant. At that point, Q is equal to the amount of product over reactant, 3 over 1, which is equal to K. So it's equal to 3. And what if you were to start with 3 products and 1 reactant? I wonder if you would soon expect more product, less product, or the same amount of product. Well, Q is equal to 3 over 1. That's the same as K. The system is at equilibrium already. Normally Q changes until it's equal to K, but if it's already equal to K, then the amount of product to reactant won't change. All right, so we've been talking about this ratio of product to reactant. Generally, that ratio is going to be in terms of molarities So that's represented by these brackets, or and that's for case C, the equilibrium constant, which is dealing with concentration. Or we can talk about K and Q in terms of partial pressures. So Kp stands for dealing with partial pressures. So for a given reaction, AAs turn into and BBs turn into CCs and DDs. We put the products on top. So C is a product, and we put the coefficient in front of that as the exponent above that, and then we multiply by the concentration of the other product times the coefficient for that other product. And then we divide by the concentrations of the reactants to the power of those coefficients. There's no additions here. These are multiplications. So for case C, that can apply to either aqueous compounds or gaseous compounds. This is concentration, the number of moles per liter, whether in aqueous solution or as a gas. So we do not include solids or liquids, which is important. You'll see that on, I think, number 2 in the homework. So let's write the Kc expression, the equilibrium expression for this reaction. All right, so Kc is going to be equal to the concentration of the product, bracket, to the coefficient in front of that product, and then times the concentration of the other product. That has a coefficient of 1, so this is just to the first power. And then we would normally divide by the concentration of the reactants, but this is solid. No solids. No liquids, or pure liquids, should be included in equilibrium expressions. So what if we had to write the Kp expression for this reaction? Instead, we deal with the partial pressure of the products, but we would not ever include solid, liquid, or aqueous solutions. Kp only deals with partial pressures. Now, sometimes you'll need to convert between Kp and Kc. Kp is equal to Kc times 0.0821 R times the temperature in Kelvin to the power of delta N, where delta N is the change in the number of moles of gas going from reactants to products. So in this case, we start with 0 moles of gas because there is no gas, it's just solid. And then we end up with 2 plus 1, 3 moles of gas. Delta N is equal to 3 in this case. All right. And sometimes you might be given the equilibrium constant for a certain reaction. A turns into B. But then you might be asked to find or to know the equilibrium constant for the reverse reaction. So instead of A turns into B, B turns into A. So in order to find that, you just flip the reactants and products. So K is equal to B over A, but K prime is equal to A over B. And how are these two K values related to each other? K prime is equal to 1 over K. If you flip around the reaction, you'll take the inverse of the K value. All right. So just kind of graphing out what we were showing in diagrams earlier, let's say that we started with all A, and we started with no B. If you achieve equilibrium for a spontaneous process, one where K is greater than 1, then soon the amount of A will decrease, and soon the amount of B will increase. But the reaction does not go to, quote, completion. It doesn't go all the way 100% into B. There's still probably going to be some A left over, and not all of the B that you expected might form. Most reactions are, going to be less than 99% products from what you expected. Every reaction has some kind of equilibrium that's going to be established. Sometimes maybe there's 10 billion products to one reactant, which doesn't appear like a lot, but it is still an equilibrium being established. And so when you establish that equilibrium, you know, A was originally turning into B substantially, and there was no B turning into A. But then, as you get less A, the rate in the forward direction decreases, and as you get more B, the rate in the reverse direction increases, until eventually those rates are equal. And you get just as many A's turning into B's as B's turning into A. And so eventually you reach that equilibrium, equal rates in the forward and reverse direction. And when that happens, the amount of A and B is no longer going to change. If every time an A turns into a B turns into an A, the amount of A is not going to change anymore. So you can see that here. When we get a flatlining, when we get no change in the concentrations of our reactants or products, then we have achieved equilibrium, flatline. So now at this temperature, with the same conditions, we should have the same amount of B versus A indefinitely for thousands or millions of years if you have the same conditions. And then what if you had started with a different condition? What if you had started with all B and no A? Predict what would happen. Would it look like this? Kind of like earlier? Nope. It should be the same ratio of B to A as in the earlier case. B to A, there's more B than A once equilibrium is established. It doesn't matter how much B or A you start with. If equilibrium is established, then you should get the same ratio in all cases. More, in this case, more B than A. A K value that's greater than 1, more product than reactant. Thanks for watching.